Sometimes we want to show that a function is convex, hopefully with a mathematical proof, and usually it's not too bad to take partial derivatives and form the Hessian, but then showing that the eigenvalues of the Hessian are always positive can be a big pain in the neck. Eigenvalues are not easy to figure out, especially in symbolic form. So one thing we can do to get evidence at least that a function is convex is to just empirically test it to see if it satisfies the convexity condition. So you just randomly pick feasible points and then a random alpha between 0 and 1, compute the function values at those 2 points, compute the interpolated x value and the function value there, and just see if it, you could record yes or no, or you could record all those floating point values and do that a few thousand times and then see how often the convexity condition was not satisfied and how much it was not satisfied by each time. So that's kind of a fun idea. How often do we need to show that a function is convex, or at least gather evidence that it is or isn't? Maybe not all that often unless you're doing some kind of pure math thing. Let's talk about neural networks. Are they convex? Well, they're actually known to not be convex, and I can show you that with this demonstration. This is called TensorFlow Playground. So we've got a data set we want to fit, and we're going to feed into it the x1 value squared and the x2 value squared, and we're going to feed those into two neurons that take a weighted average or weighted combination of these two inputs and then feed it through a sigmoid function. So I'm going to start training the network here, and you can see that it got a pretty good solution, right? It classified the blue points as blue, and it classified the orange points as orange. And it seems to have a lot of weight on the output from this neuron and not very much on the output from this neuron. So how can we use this to argue that the problem is not convex in the weights that it's using on the edges here? Think about that. Well, there's nothing special about this neuron being the first one and this neuron being the second one. I would get just as good of an answer if I picked up this neuron and moved it up here and moved this one down here and kept the weights attached to them. So there's obviously more than one optimal solution because I can just move neurons around as long as I keep all the weights. But in between those two perfectly equal optimal solutions, you could say instead of moving neurons around, I'm going to convexly interpolate between these two. Like if this weight is negative 2.1 and this weight is 0.34, I'm going to form a convex combination. So like alpha equals 0 would be these weights, alpha equals 1 would be the weights switched. So in between, you'd have this one not as strong and this one not as strong the other direction. And the objective function would probably not be as good there. So it's like you've got a minimum here and a minimum here, and you would have to go kind of over a mountain pass in between those. So we know neural networks are not convex. The question is, are they reasonably convex in typical usage? And that's a really interesting story. It's really hard to visualize because they're in really high dimensions. So here's a nice interesting paper about visualizing the kind of objective function value of neural networks. Let's talk a little bit about Newton's method and convexity. Newton's method seemed great, right? Predicts where the optimum solution is for quadratics exactly, and for things that are near quadratic, then it predicts it pretty near, we think. But what if it's a quadratic that's not convex? Or what if you're far away from the optimum and you've got a little non-convexity or a big one? What can you do about it? Well, you could say, well, negative eigenvalues are the trouble here. Maybe I can do something to the Hessian to make the eigenvalues not negative anymore. Maybe it won't be the Hessian still, but maybe I can do something so that matrix that I'm inverting won't have negative eigenvalues. And it turns out if you add a scalar times the identity and make the scalar big enough, well, just adding a scalar times the identity shifts all the eigenvalues up if the scalar positive. And if you do that enough, then all the negatives will become positive. And in some sense, that gives you now a positive definite matrix. And when I first heard this idea, I was like, wait a minute. Why should we have any faith that the search direction we get from this makes any sense in the context of the problem? I mean, you're just taking a Hessian and just adding a diagonal matrix to it. What's that going to do to the search direction? I don't trust this at all. So here's idea number 2. What if we say, well, we can't always trust the search direction from the Hessian because the Hessian might not be positive definite. we usually kind of trust the steepest descent search direction. So we could say, let's take the Hessian search direction, or the Newton search direction, which actually we shouldn't trust all that much if there's non-convexity going on, and the steepest descent search direction. And since there's an I here, we could also write that as an I inverse to match the H inverse, and just take a weighted combination of the two. And maybe when we're not trusting the Newton's method so much, we give that less weight. And when we're not trusting, or when we're trusting the Newton's method more, give this more weight and that one less weight. So to me, this sounds like a reasonable idea. We can smoothly interpolate between the Newton search direction and the steepest descent search direction. So think about how that idea relates to this idea. Are they basically the same? Are they exactly the same? Well, you almost want to say, oh, let's pull the multiplier of gradient of f out, and we'll get scalar times h inverse plus scalar 2 times I inverse, which is not the same as this because the inverse matrix of a sum is not the sum of the inverse matrices, but it's that same idea. We're kind of saying here, if I use a huge scalar, that's like swamping the Hessian, right? I'm just adding something huge. This is going to be the dominant term, and then take the inverse of that. And so that's going to be basically the steepest descent search direction. So these two ideas are mostly the same idea, just kind of written with different parameters. And then another idea is to say, well, adding the identity to the Hessian, how do I know that I should add the same thing to each diagonal element? So you could say take the existing diagonal of the Hessian and use that, because that way if one element is typically small and another element is typically big, you're kind of automatically adjusting to the scale of each variable. And that's kind of what the Adagrad algorithm does that we kind of talked about earlier. These ideas of kind of convexifying the approximation, the Taylor polynomial approximation, are related to the Levenberg-Marquardt algorithm, which is a common thing for solving nonlinear least squares regression or curve fitting problems. And it's related to ridge regression. In ridge regression, we have the sum of squared residuals, and then we add the sum of squared coefficients. And what does that do to the Hessian? That's adding a term to each of the second derivative, second partial, like x1, x1, x2, x2. And so that's adding a diagonal, and someone once thought, oh, that's like adding a ridge, kind of like this, to the matrix. So that's why it's called ridge regression. Desmos is a fun tool to use, and it has a regression feature built in that can do. Sorry, I just get so emotional about this. It can do nonlinear regression. It can do multiple regression. It's kind of neat. And they have a really interesting page that describes how they use the Levenberg-Marquardt method and all kinds of interesting other safeguards. So I recommend reading that if you're curious about that kind of thing. And next we'll talk about why we love convex and concave functions so much.